Hello, welcome again. See what we have seen in last lecture was loop antenna, is it? And now we are going to start with this aperture antenna. See, already we had a discussion about that aperture antenna. Aperture means what basically it is a kind of area we are talking about. Right. So the antenna which has a surface area and which is receiving the signal and radiating the signal, we can call it as an aperture antennas. Right. So look at the definition. What it is written: an antenna with an aperture at the end. Is it? For example, see if you are considering two-wire transmission line, and somewhere at the end, if there is an area, then obviously that area which is formed along with the transmission line is called aperture antenna. Is it? So waveguide is the best example. What do you mean by that waveguide? So whenever the waveguide term come, what do you need to think about? A hollow pipe. Is it? A hollow pipe is the best example of waveguide. So you will study those waveguides in next year. Is it? When you start with microwave theory, you will understand what is waveguide, what are the applications, or what are its limitations. Is it? You will understand everything about waveguide in microwave theory. Is it? For the time being, in antenna theory, understand that the waveguides are like a hollow tube. Is it? At one end we need to feed the signal, from the other end we will get some radiations. Is it? So waveguide can radiate. See, waveguide are radiators, but I am not saying waveguides are efficient radiators. They are just radiators. They can radiate signal. They have ability to radiate the electromagnetic waves. That's what the important thing. Is it? So that's why if they are having ability to radiate the electromagnetic waves, they can work as an antenna, and that's the reason we are saying it is an antenna. Is it? So best example for aperture antenna is a waveguide which has a nice surface area. See, the edge of transmission line when terminated with an opening, this is a transmission line, when it is terminated with some opening area, then it can radiate the energy. See, I am still saying it can radiate the energy, and that's why I am saying it as an antenna. I am treating waveguide as an antenna. Look at this. This opening, which is an aperture, makes an aperture antenna. So what we will say to those antennas are referred as aperture antennas, which terminate with some surface area, which ends with some surface area, and which has an ability to radiate the signal. Those are aperture antennas. Is it? So basically aperture antennas are classified in three types. Those are not actually types, but it is a classification. First one is waveguide antenna. Waveguides can transmit, so I am calling them as an antenna. Second one is horn antenna, and third one is slot antenna. We'll discuss them one by one. Is it? So let's first discuss about waveguide antenna. So waveguide antennas are nothing but a simple waveguide which holds an ability to radiate the signal. So if it is radiating, yes, it is antenna then. A waveguide is capable of radiating the signal or radiating the energy when excited at one end and opened at the other end. Obviously waveguides are open at the another end with some surface area and fed with at the other end. The radiation in waveguide is greater than two-wire transmission line. If there is a two-wire transmission line, it will radiate, no problem. But when it is terminated with some surface area, it will radiate more. What we are calling that? We are calling it as an waveguide. Is it a simple transmission line? Yes, it is radiating, no problem. But if I want more radiation, then what I will do? I will terminate that transmission line with some surface area. Is it? A transmission line terminated with the surface area are called waveguide. Is it? So that's why it is written that waveguide has a greater transmission if I compare them with a two-wire transmission line. So what is the frequency range? Look at this. Frequency range is up to 300 gigahertz. Look at this. Isn't it very large? This is a large frequency range over which waveguide can operate, is it? So that's why it is treated at UHF and EHF frequency ranges. So up to 300 gigahertz, obviously it is a large frequency range, is it? So this is about waveguide antennas. Now see, if there is a picture of waveguide antenna, look at this. Now what this picture shows, this is one end, look at this, this is one end, and somewhere here at this point there is another end. Wave is fed at this point, it travels through this waveguide, and somewhere from here it will radiate, is it? That's what the actual thing, is it? It will start radiating. So it is a waveguide. I didn't say it will radiate efficiently. It will radiate greater than 2-wire transmission line. It will radiate, but not as much as efficient, is it? So why it is not as much as efficient? Obviously because of this VSWR, that is reflection. See the line, it is written, this waveguide will with a terminated end. Look at this, the waveguide will act as an antenna. Obviously it is radiating, so it is antenna for me. But only a small portion of energy is radiated, while large portion is reflected back. I say it is a radiator, it is an antenna. But reflection is more in that antenna. In waveguide antenna, reflection is more. What we need radiation more, but here reflection is more. Reflection is more means VSWR will be large, isn't it? That is voltage standing wave ratio. Already we had a discussion about what is VSWR, is it? So if there is no or less impedance matching, the waves reflect back from the load or from the terminated thing, whatever you connected at the output side, is it? So that reflected wave, the ratio of maximum and minimum of that reflected wave is called as a VSWR. The standard value for VSWR is, it's not standard, but tolerable value is always 2, is it? So VSWR 2 is tolerable for all the RF systems. So in the waveguide antenna, VSWR is large because of large reflection. Large reflection, small amount of transmission, but transmission is there, and that is good as compared to the 2-wire transmission line, is it? So value of VSWR is high. Value of VSWR is, it means what? Diffraction around the waveguide is there. Obviously VSWR is there means diffraction is there, and that's why poor radiation is there. And when there is a poor radiation, it means the radiation pattern is non-directive. Look at this, radiation pattern is purely non-directive. Non-directive means this waveguide will never radiate a signal in a particular direction, is it? So when signal come out of that waveguide mouth, what I can say, the terminal or the end of the waveguide, the signal, the RF wave will spread around. It will not be directed to the particular direction, is it? So that's why it is non-directive. So non-directive is generally referred as omnidirection. Isn't it? Omnidirectional. Omnidirectional means what? Omnidirectional means same energy in all the directions. Agreed? So here, yes, things are written here. Look at this. Radiation pattern under the title. A radiation of a waveguide antenna is poor. Obviously, radiation is poor, and pattern is non-directive. Now, what does it mean by that non-directive pattern? Non-directive means omnidirectional. Omnidirectional means what? Which has no certain directivity and radiate in all directions, is it? So that waveguide antenna, is it? Now I am not referring it only waveguide, I am calling it as waveguide antenna because we have classified, we have included in the types of antennas, is it? So it has a non-directive, or what I can say, omnidirectional radiation pattern. Omnidirectional, non-directive, it means it has very limited and specific applications for this waveguide antennas, is it? Limited and specific. Let me write it here. Limited and specific applications are there with this antenna. Now, apart from that, let's check. Apart from that, we have that kind of radiation pattern. Look at this. Okay, are we here? Sorry, I'm sorry for the interruption. So we are in the radiation pattern of that waveguide antenna. Basically, look at the radiation pattern. It is purely omnidirectional. Let me have this. Let me have pen. And look at this. This is actual radiation pattern that I was talking about. Look at this. Purely omnidirectional. So as if it is purely omnidirectional, it is less directive. The word they have used is less directive. Now, what are the advantages and disadvantages of that waveguide antenna? So if I want to write advantages, then radiation is greater than 2-wire transmission line, as I told you so many times that it is good, or what I can say, it is better than 2-wire transmission line, but it is not as much better as we are expecting actually. And radiation pattern is omnidirectional. So I am putting it as an advantage or benefits that I am getting. So what are the disadvantages? Disadvantages is VSWR is very high and obviously it has poor radiation. See, greater radiation as compared to 2-wire transmission line, but it is poor radiator if I am saying it as an antenna. So what are the applications? I told you that limited and specific applications, microwave and surface wave radars. Those are basic applications. So I hope you have studied that radar thing in 5th or 6th chapter. Look at this. Now the waveguide antenna has to be further modified to achieve better performance. So waveguide antennas, I said it is a good option to the 2-wire transmission line, but it is a poor radiator. Look at this. Advantage is this and disadvantage is this. So if I want to increase its radiation power, or what I can say directivity or radiation capability, then what I need to do, I need to change its aperture. I will change its physical structure. If I change physical structure, the new antenna that I am coming up with, that is horn antenna. Just modify waveguide antenna, you will get horn antenna. So what kind of horn antenna, how horn antenna will look like? Here we will have a look. Now we are going to start with this horn antenna. To improve the radiation and directivity, basically radiation efficiency and directivity. If I want to improve from that waveguide antenna, then I am coming up with a new type of antenna, that is horn antenna. So what is there in horn antenna? Basically the horn antenna, look at this. This is a transmission line. It is an actual on-site view or practically used antenna, horn antenna. Look at this. Its mouth is flared, or the aperture is flared like this. Flared, that's what the aperture is flared, so that I can get maximum radiation. Is it? The aperture is flared to get maximum radiation. Now what exactly they have written? Let us check. Now see, this can be termed as flaring. I told you, flare the mouth of waveguide, you will get horn antenna. Right. Now frequency range is about 30 gigahertz. Now for a waveguide, how much it was? It was 300 gigahertz. Obviously it's a waveguide, it's a hollow pipe, can work at higher frequencies. Now I am flaring it. If I am flaring the mouth, I am flaring the aperture, then obviously the operating frequency range will decrease, radiation will increase, the range will decrease. Isn't it? It's a simple common sense. Now let's look how exactly it is. Now here what we have is this. This is just a stand, a support to the antenna. This is actual antenna. Here I am going to feed this antenna. Look at this. Here I am going to provide a feed to this antenna. So this is feed, and I am interested in that structure. Look at this. It is purely flared, is it? उसका जो mouth है उसको हमने sprayed कर दिया. So what they have written, that when the energy of a beam when slowly transformed into the radiation, the losses are reduced and a focusing of beam improves. A horn antenna may be considered as flared out waveguide. Is it? So waveguide is flared out, it becomes a horn antenna. So as I told you so many times that the first antenna was developed, designed and implemented by Marconi. Is it? Is it? It was Marconi who invented the antenna. It is the name of scientist. But before Marconi actually published his work on antenna. Is it? Initially, or first time Marconi published his work. But before publication of Marconi's paper or the work, Dr. Bose, I told you Dr. Bose, one Indian scientist, Jagdish Chandra Bose, who worked on that horn antenna. Is it? He invented horn antenna and he worked on 40 gigahertz with this horn antenna. Is it? But his work was not published. He were busy in invention and improvement of that horn antenna. Meanwhile, what Marconi started? He invented that wire antenna. He invented that wire can transmit and wire can receive. He published his work. And that's why in all the books, it is written that Marconi was an inventor of antenna. And in some foreign universities, still there is a controversy about that Marconi and Dr. Bose, who invented antenna. Is that? So, we are not stretching the topic of who invented antenna. The thing is, horn antenna is a sprayed version of waveguide and it can handle large amount of frequency or large amount of radiation. The range obviously reduces to 30 gigahertz. Even if I am getting a less range, but the radiation intensity is more. Okay. So nowadays actually we are using antenna as per our application. So that's why if application is up to 300 gigahertz, generally people go for that horn antenna. Is that? So this is about horn antenna. Now let's check what improvements are there or what is further classification. Okay. Now those simple horn antennas are further classified as sectoral horn. Look at this. One is sectoral horn, another one is pyramidal horn, and third one is conical horn. Is it? Now those types, actually there is no need to discuss those types because by common sense we can clearly say that look at it, sectoral horn means it is spread in either E plane or in H plane. Look at this horn, the first one. Okay, let me now look at this page that I'm to this image actually. This image, it is spread in this direction, that is in H direction. Look at its height, that is vertical direction, it is very less, but it is spread more in horizontal direction. So that's why it is H plane sectoral horn. And what about V plane sectoral horn? Look at this. Let me take that view also on a single page. Now look at this. Here the antenna or the horn antenna is spread more in horizontal, so that's why it is H plane. Here the antenna is spread more in vertical direction, so that's why it is E plane sectoral horn. So those are types of sectoral horn antennas. So what is next type? Pyramidal horn. So what is pyramidal horn? Look at the mouth, the open end, it is clearly rectangular, and look at the 3D shape. The 3D shape looks like a pyramid, so that's why it is called pyramidal horn. Is it? Next type is conical horn. Look at the conical horn. Its end mouth, or what I can say, end is circular and the shape that it acquires is a cone. So those are the types of horn antennas, and that's why I said there is no need to discuss those types. Even by just observing the figure of those horn antennas, we can easily understand what are those actually. Is it? Look at this, one is sectoral, pyramidal, conical and E-plane. Yes, that's what it is. Now apart from that, there are combinations of all those antennas also. What are the combinations? See, that is cross horn, hog horn, and the radiation pattern is also given. So we are not going into that, but we will definitely see what are the advantages and disadvantages as well as the applications. So let's have a look of advantages. What are the advantages? See, small minor lobe are formed. The horn can form a small large main lobe and very small minor lobes are there because it is highly directive, na? So impedance matching is good and it has large or greater directivity. Those are some advantages or benefits I am getting from the horn antenna. Is it? So beam width is very small. Is it? Narrower beam width means beam width is small. It produces a sharp beam. Is it? Standing waves are avoided. Standing waves are very negligible. There is no reflection at all because it's a flared horn antenna. The waveguide is flared completely, so that's why obviously I'm not getting any standing waves. So VSWR will be very less. That's what it is. Now, what are the disadvantages? Disadvantages, it takes actually a lot of efforts to design that horn antenna. So designing a flare decides a directivity, and that's why I said it takes a lot of efforts. Is it? Because जितना आप flare करोगे उतना आपको directivity में changes मिलेंगे. Is it? So depend on the directivity, I need to flare that. That's why designing is very critical. So that is one of the most important disadvantage. Now flare angle and the length of the flare should not be very small. Is it? If the flaring is very small, obviously it will act as a waveguide then. Is it? Then what's the use of having a new kind of horn antenna? Is it? So that's why the length and the flaring should not be very small. अगर इतना small रहा तो radiation क्या करेगा? Waveguide की तरह ही काम करेगा ना? Is it? We flare and we create a new horn antenna. अगर हम flare कम कर रहे हैं तो it will act as a waveguide antenna, which has a lot of disadvantages. Very less radiation is there. Is it? Now, what are the applications? It has large astronomical applications and basically it is treated as a microwave antenna. So in microwave or at microwave it is used. Is it? Basic application is microwave and astronomical. So even if you write 2, then also it is sufficient. Now this is all about horn antenna and waveguide antenna. The next type of antenna is a slot antenna. It is really interesting to understand slot antenna because there is a surface and you need to make a slot on that and it forms an antenna. Is it? But we'll check those slot antennas in next lecture. Is that? Thanks a lot.